Hey there, ladies and gentlemen. I am going to try to hit the notes we didn't do on the second half and then pause and have some questions built into that. We've got a whole lot of stuff already. We have different types of covalent bonding, whether it's shared equally or unequally shared with covalent. We talked about electronegativity and the trend and how it increases as you get closer to flame, and how about there can be dipole moments and polar molecules. We're going to hit a bit more on this. When a molecule is unevenly distributed, it is polar. I think we need to hit a couple of examples later on in these notes on that. Um, Not quite here. We're looking at some molecules like Lewis dot structures we already have drawn. We're talking about ion size. We talk about things we're skipping. Anything with enthalpy in it or bond energy, enthalpy or bond energy, we are still skipping. Um, we talk about covalent bonding, bond enthalpy. Skipping that. We talked about that so much. I'm not thinking about it again right now. Talked about metallic bonding, a sea of electrons, alloys, substitutional versus interstitial. Substitutionals when you swap one out for another. Interstitials where it gaps in between. It's in between. We spent a good deal doing Lewis dot structure. That's pretty much what your first one was, a whole lot of Lewis dot structures. But let's look at these horrible drawings and at the same time talk about this chart you have. Okay, so this chart you have, let's label a couple of these as polar, and they are always polar. I'm gonna just put a blue decent sized dot. This one is always polar. 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 This one is not always polar right here. Not always polar right here. So I've just kind of put little marks on the ones that are always polar. And you notice the ones that are always polar, they have an unshared pair of electrons that is not balanced out across the central atom. Like look at the top element, the top one, that bent angular one. You have a pair of electrons, and on the other side you have bonded atoms. That is not balanced, so that's polar. The trigonal pyramid has a bonded pair, three bonded atoms, and then in another direction, a pair of electrons. Not balanced, and therefore polar. Off balance equals polar. Bent or angular a second time, again off balance because there's pairs of electrons, and on the other side there's bonds. That would be polar. Now, as we look down to the next couple, it's a little bit harder because you're not as familiar with them. And this is really where I suggest you spend some time playing with that PhET, the molecular model PhET, and getting better at it. But the seesaw, the T-shaped, they are both off balance on the opposite side of the atom from the electron pair are bonds. For both T-shaped and seesaw, opposite of the electron pair are bonds. Now in linear, what's opposite of the electron pair? Opposite from the atom is more electrons. And the problem with this drawing is it's two-dimensional when it really should be three-dimensional. And they're attempting to show three dimensions there. You can see the triangle dashes and the triangle solid. That's forward and backward. One of those is forward, the other is backwards. And the three pairs of dots, are in a triangle position, thus the original name, trigonal bipyramidal. They're a triangle positioning around the central atom, and they are perfectly opposite of each other, so they cancel each other out. And linear, in that case, the linear, I should just kind of direct your attention. This linear here is nonpolar because the electrons are balanced out and the atoms are balanced out. In the octahedral family, we kind of go back and forth, don't we? We have the octahedral, which is perfectly balanced. Every element is canceling every element out. And then square pyramid, it's not balanced. The square is balanced, but if you go up and down, you have a pair of electrons, and then you have a bonded atom. So that one's off balance, that one's polar. Square planar, you have four atoms bonded, and then two pairs of electrons. That one's balanced because the pairs of electrons are opposite of each other. and the bonds are opposite of each other. And then the T-shaped, again, T-shaped is off balance. Opposite of that pair of electrons would be an atom. And then the linear is also nonpolar. Now, when we talk about polar and nonpolar, here it's not terrible to see, but as you go to some of the other slides, some of the other drawings, it can be a little bit harder. But okay, let's move on. So the next thing we're going to talk about is called hybridization. Hybridization is when the atoms orbitals blend together. I need the time here. There we go. When the atoms orbitals blend together, so it kind of depends on what the atom has available. So let's think about carbon in the CH4. Carbon, if you draw its orbital, it is 1s2, 2s2, 2p2. That's 1s2, 2s2, 2p2. I want you to draw the orbital diagram for that. You'd have 2 electrons in the 1s2. You'd have 2 electrons in the 2s2. And then when you get to the p, you'd have these 4 orbitals, those 4 boxes. When I say orbital diagrams, I'm talking about the boxes. You put arrows in the boxes. So in the 1s, you have 2 arrows. In the 2s, you have 2 arrows. And when you get the 2p, since carbon's 2p2, you have 2 arrows, and they each go in one of the boxes, right? Okay, so we have 2, 2, and then a spread out 2 in an empty box. Now this carbon atom has a configuration. That configuration, 1s2, 2s2, 2p2, is the, hey, I'm carbon and I'm all alone. I don't have any friends. I'm not sharing electrons. I'm just a carbon atom. In methane, CH4 is the carbon atom all alone. No, it's not. It's bonded to the hydrogens. And that means that this configuration, 1s2, 2s2, 2p2, is no longer true. I know I spent all this time explaining it, but it's no longer the case. First, I wanted to make sure you understood what carbon as an atom by itself was like. And now we're going to talk about carbon as a bonded atom and how everything changes. The s orbitals and the p orbitals, like you see in this diagram, will blend together and change. And before we go to the next slide, let's make sure we answer these questions. What's the shape of a methane molecule? CH4 would be tetrahedral, be carbon in 4 directions. What are the bond angles? I think those bond angles are around 109. At least that's what my memory says. What is the valence electron configuration of carbon? We just did that, 1s2, 2s2, 2p2. Why can't bonding orbitals for methane be formed by overlapping atomic orbitals? So if it's going to make 4 bonds, how many electrons are being shared? If it's going to make 4 bonds, how many electrons are being shared? Must be 4. But when we look at that diagram I had you draw a second ago, 2 arrows, spread out 2 arrows, there's only 2 electrons in there that aren't already paired up. And the Pauli exclusion principle says that a region of space, which we call an orbital, can only hold 2 electrons. So the way carbon is drawn, we don't have enough space for the bonding. So that must not be the right drawing. 1s2, 2s2, 2p2 orbital diagram must be wrong for when it's bonded together. And that's where hybridization comes in. In hybridization, the orbitals that we know, the s's and the p's, will hybridize or blend. They'll blend into each other. And so we have a mixture of orbitals, of s and p orbitals. So this is beautiful, isn't it? Those s and p orbitals blend together to make new and weird frickin' looking shapes. So it is making 4 bonds, which means there must be 4 electrons available to bond. In the valence shell for carbon, there are 2p orbitals and 2s orbitals. And the 2s has 2 electrons and the 2p has 2 electrons for a total of 4. These are the 4 electrons that are bonding. But they can't still be in s's and p's like we traditionally know because the s's are already paired and they can't bond. So instead, when they get close to the hydrogen atom, those four shapes get twisted and bent around to make these four new shapes, which you don't need to know the look of the shapes, but you need to know that these are called sp hybridized orbitals. And sp hybridized orbitals, when they hybridize, these four shapes are going to hybridize into what are called sp3 orbitals. They're called sp3 orbitals. You notice there's four of them. There are four sp3 orbitals. Now, I was always confused by this when I was a young lad learning this. And so I'm going to teach you my trick. S, there's only one of those. P, there's three of those. S, and then three P's. sp3 is a total of 4. How many bonds do we have on this? We have 4. So I just really counted the number of bonds, and then I knew the type of hybridization that was occurring. Since there are 4 bonds, it's a sp3 orbitals. All right, that was my trick for remembering it. Now, as I have grown and become more and more wise, I realized I should actually be talking about the electron region geometry, like how many directions are the electrons in. So whether it's tetrahedral, which is 4 directions and therefore sp3, or if it's bent is 2 and 2, right? 2 directions, 2 pairs. That's also still sp3 because these electrons arrange themselves in the same shape as the tetrahedral. So if you use the electron region geometry, it's pretty easy to figure out the hybridization. And so that's what's going on here. Now they're talking about what if it's this particular drawing, sp2 is, come on, Russell. It's a trigonal planar. This is a trigonal planar drawing. It's got bonds going in 3 directions, so it's an sp2 hybridization. It's got bonds going in 3 directions, so it's sp2. I'm going to say that slower. It's a single S, and it's 2 P's, right? It's an S and a P. S to the first power, P to the second power is a total of 3 directions. So if you have bonds in 3 directions, those orbitals hybridize into sp2 orbitals. Okay. What if you only have bonds in 2 directions? Then an s orbital and a p orbital must be blending together to make an sp orbital. That's 1 s and 1 p. That's 2 directions. That's the linear shape, the original linear shape for hybridization. Hey, so basically it boils down to this. If it's going in 2 directions and only 2 directions, it's sp. If it's going in 3 directions, it's trigonal planar, it's sp2. If it's going in 4 directions, it's tetrahedral, it's sp3. Now you notice there's a gap and then it deals with 5 and 6. That's because the 5 and 6 are not 100% agreed upon. Some people think there's trigonal bipyramidal sp3 involving the D, and some people don't. And because there's still an argument on this, we're not really going to teach it. There's a huge quantity of physical chemists that think they exist, and there's a huge quantity of people that don't think it exists. But it is a theory that's been out there for about 25 years, and it's in some debate still. So it's not going to be assessed. You're never going to have to look at a seesaw and say seesaw is sp3d. But you may have to know it for any of the tetrahedrals, trigonal planars, or linears, the regular linears, none of those wild ones. So as we look at diagrams and do Lewis dot structures, we can now say, okay, hey, look, this thing is bonding in 4 directions, and it is an extra pair of electrons. It's tetrahedral, or it's trigonal planar, or it's linear. And this is merely saying that the s orbitals and the p orbitals are blending together for bonding. Now we're supposed to draw some Lewis dot structures. I'd like you to draw these Lewis dot structures on your own, and then we'll discuss them next class. Okay, single and double bonding. So that single bond, the first bond that is formed, is called a sigma bond. And it's a pretty low energy, easy bond to form because it's a direct connection between the two atoms. The second bond, though, is far more complicated, and it's called pi bonding. And it actually exists around the sigma bond. And I'm going to show you all a video explaining that a little bit more. But if you have a single bond that, or a first bond formed, that's a sigma bond. And then every second or third bond is called a pi bond because it's in a different energy zone. Excuse me, I had the hiccups, shocker. So let's draw a molecule here. I'm not going to try to draw on the screen too much. Let's do CO. See, this is why I wasn't going to draw C2H2. Oh, that's so ugly. So we'd have hydrogen bonded to carbon, bonded to carbon, bonded to hydrogen. Neither one of these carbons has enough electrons, so it doesn't just have to double bond, it has to triple bond. So I've color-coded these just for our conversational purposes. A first bond that forms is a low-energy bond called a sigma bond. So between the hydrogen and carbon, there is a sigma bond. Between the other hydrogen and carbon, there is a sigma bond. They are orange. Between the two carbons, the first bond that formed is the lowest energy bond, which is called a sigma bond again. Here I've color-coded it still orange. But for carbon, there has to be double bonds and even a triple bond to make this molecule work. So the blue and the green are pi bonds. They're higher energy bonds. They're harder to form. And so between the two carbons, there's one sigma and two pi bonds. Okay? Pretty much, if you just count carefully, it's easy to figure out how many sigma and pi. If it's a single bond, it's a sigma. If it's a double bond, it's a sigma and one pi. If it's a triple bond, it's one sigma and two pi bonds. Sigma is lower energy, pi is higher energy. It's harder to achieve. We don't actually talk about bond order anymore. This is Mr. Shangra last year putting a note in here. Bond order is a really complex calculation that kind of got eliminated from our world. Here's some diagrams showing the hybridization and showing the sigma and pi bonding. This is a great one right here. So the first bond is forming, go back to my color coding, between these two orbitals. There's a bond forming there, and that simple low energy bond is called a sigma bond. Good. And then the second bond is forming between these p orbitals. That's one of the pi bonds. Notice they're both on the y-axis. They're up and down. And then the third bond, or triple bond, is forming between this one, and it's going to be hard to show that there's another one hiding back there. And in the front, this one's in the front, and this one's in the front. And so you have three bonds. The sigma is the green in the middle. There's a pi bond above and below, and I've got to change color so you can see where I'm writing. This is one pi bond in blue, and then this is the other pi bond in green. And it's pretty complex there, but we don't get into drawing these. We don't really get into assessing any of these weird drawings. But just to say that the sigma bond is simple and the pi bond is a much more complicated bond. And since this has, that's actually what I was just drawing, the triple bond, it's got one sigma and two pi between the carbons, and then a sigma between the carbon and the